All right, we are talking about section 6.1. I'm going to edit my pen setting really quick. Talking about section 6.1, we're going to graph systems of equations. So we've been looking at graphing just one equation. Now we're going to graph something called a system of equation. So by the end of this video, you should be able to determine the number of solutions a linear system has and solve systems of linear equations by graphing. Graphing it is just one way we can solve them. So this chart right here is a little bit of an introduction to this topic. So there's different types of solutions we can get, different numbers of solutions. So we can either have exactly one solution, infinite solutions, or no solutions. If you get exactly one solution, we call that consistent and independent. So consistent meaning there is a solution, and independent means there's one solution. They're independent of each other. So if you have one solution, your graph should look something like this. If you have infinite solutions, we call that consistent and dependent. Consistent meaning that there is a solution, and dependent meaning that the solutions depend on one another. You can see in the graph here, it looks like there's just one line, but really what that means is our lines actually line up with one another. So in the exactly one solution, they cross once. That is my solution. In the infinite solutions, they cross everywhere. They line up specifically with one another. Therefore, there are infinite solutions. And then we have no solutions. We call that inconsistent. So there are no solutions here. The graph looks something like this. You might notice these are parallel lines. That's what we call inconsistent systems that have no solution. So if we come on down to example 1, we're going to use the graph at the right to determine whether each system is consistent or inconsistent, and if it is independent or dependent. So first of all, y equals 2x plus 3. That's this blue line right here. Y equals 2x plus 3. Here's my line. Then I have y equals x minus 5. That's that purple line on the screen that you see here. So my lines here, they don't actually cross each other on this graph, but they're also not parallel. If I continued these lines off the graph, you might see that they would eventually cross one another, something like that. So these are, in fact, having one solution. That's true in this case. I'm going to erase those. So if they have a solution, that means, first of all, that they are consistent. Oops. They are consistent. Secondly, I'm trying to figure out if they are independent or dependent. So if I scroll back up to this chart, again, if I have exactly one solution, it's consistent and it's independent. The solutions are independent. So here I'm going to say independent. All right, let me fix this really quick. It got a little bit off. There we go. Sorry about that. So now, on 1b, I have y equals negative 2x plus 3 and y equals negative 2x minus 5. Before I even look at the graph for these, you might notice, it's okay if you didn't notice this, you might notice that these are both in y equals mx plus b form, and they both have a slope of negative 2. Remember, we talked about lines that have the same slope, those are parallel. So if I look over at my graph here, y equals negative 2x plus 3 is this green line, y equals negative 2x minus 5 is this red line. These lines are parallel. They will never meet each other, excuse me. They run directly beside one another. So are they consistent or inconsistent? Well, they never cross one another. So in fact, they are inconsistent. If they have no solution, if there are parallel lines, they are inconsistent. So I'm going to say that these are inconsistent. All right, then if it's independent or dependent, you might notice from the chart, it doesn't say whether the graph with no solution is dependent or independent. That's because there's no solution, so I don't even need to say whether or not it's independent or dependent. So my answer on 1B is just inconsistent. So now instead of looking at a graph, we're going to actually graph each system of equations and determine the number of solutions that it has. If it has a solution, name it. So on 2A here, I have two equations that I'm given. These are my systems. I'm going to go ahead and graph each of these. So first of all, in order to graph them, I want to get them into y equals mx plus b form. That's going to be my easiest bet here. If I can get my pen to work, that'd be cool. All right, I want them in y equals mx plus b form. So if I have x minus y equals 2, I want to get y by itself. I'm going to subtract x from both sides, end up with negative y equals negative x plus 2. Now to get y by itself, I need to get rid of that negative 1 that's hanging out in front of that y. I'm going to divide both sides by negative 1. So I end up with y equals negative x over negative 1 is just x. Those negatives cancel. 2 divided by negative 1 gives me negative. So on my graph over here, I'm going to graph this. My y-intercept is negative 2. And then my slope is 1. So I'm going to go up 1 over 1, up 1 over 1, up 1 over 1. When you are graphing systems of, well, that dot got a little bit off. When you're graphing systems of linear equations, it may be helpful to use more dots than you need. You want a very specific line when you're solving for linear equations. So I would suggest doing more than you think is necessary and then connecting your lines. It'll keep your line a little bit more intact there. All right, so now I'm going to solve 3y plus 2x equals 9, and I want to graph that. So 3y plus 2x equals 9. I'm going to subtract 2x from each side. I end up with 3y equals negative 2x. 2x plus 9. Now to get y by itself, I'm going to divide both sides by 3. And I have y equals negative 2/3 x plus 9 divided by 3 gives me 3. Okay, so now my y-intercept is at 3. And my slope is negative 2/3. So I'm going to go down 2 over 1, 2, 3. And there I have my first dot. Down 2 over 1, 2, 3. And there I have my second dot. So now my line is going to look something like this. Kind of messed it up. Let me fix that. Didn't even realize I missed the first dot completely. How about that? There we go. Something like that. So they actually cross in one place, and it's at this stop right here. I'm going to change the color so we can see that a little bit easier. Right there. So my slope that allowed me to count up to that point, I'm going to erase so we can read the numbers. You'll see that the actual point there is at 3, 1. So if you look at that actual point, let me change that. This is at 3, 1. You can always double check this by plugging it in to make sure you have a true statement. So 3, 1 means that my solution then, I'm going to write it down here, x equals 3 and y equals 1. That's what my solution is. The point where they cross is 3, 1, so my solution is x equals 3 and y equals 1. All right, I want to caution you again, be very careful when you're graphing these. It's easy to mess this up. Make sure you have dots at both places. That means that that point where they intersect is indeed on, or is indeed the solution, excuse me. So I counted up 1 over 1 to get to this point. I counted down 2 over 3 to get to this point. So I can check to make sure that is in fact 1. So now in 2b, here's my system of equations. I have y equals negative 2x minus 3. That's my first equation. Lucky for us, that one's already in y equals mx plus b form. So I'm going to go ahead and graph that. My y-intercept is negative 3. My slope is negative 2 over 1, so I'm going to go down 2, 1, 2 over 1, down 2 over 1, down 2 over 1, and so on. To make this more exact, I can also go up 2 and back 1, kind of like what we talked about when we do rise over run. So I'm going to go up 2, back 1, up 2, back 1, up 2, back 1, up 2, back 1. So now I have quite a few dots there, and I can go ahead and connect my line. So my line should end up being something like that. All right, so now I'm going to graph the other line, 6x plus 3y equals negative 9. So I have 6x plus 3y equals negative 9. I want to get this into y equals mx plus b form, so I'm getting y by itself. I subtract 6x from both sides. I'm left with 3y equals negative 6x minus 9. Now to get y by itself, I'm going to divide both sides by 3. And I end up with y equals negative 6 divided by 3 gives me negative 2x. Negative 9 divided by 3 gives me negative 3. So now on my graph, you'll notice we end up with that same line that we started with. So what's going to happen is if I ended up actually graphing this one out, my y-intercept would be negative 3, my slope would be down 2 over 1. It ends up lining up with itself. That I get the same line. So again, what does that mean? Well, let's scroll back up to double check. Remember, when we get the same line over itself, that means we have infinite solutions, and that our terminology is that it's consistent and dependent. So here I'm going to say that there are infinite solutions, and that is because the line lined up with itself. Oh, wow, I spelled that wrong. Sometimes you guys are bad at spelling, but I'm definitely bad at spelling sometimes too. Infinite solutions. There we go. All right, so now you should be a little bit more familiar with systems of linear equations and some different types of solutions you